wide field image after background subtraction using the rolling ball algorithm available in Zen software. While on the right, the image was processed with photo editing software from Adobe, using a series of adjustment steps to the original wide field image. The settings used in this image were 90% dehaze, 80% clarity, 80% texture, 80% blacks, and 10% contrast. In both examples, most of the haze in the processed image is eliminated to give us better image contrast. Like unsharp masking, the background subtraction function is also available in Zen imaging software as a post-processing method. With this function, you can remove smooth background or correct uneven illumination with the so-called rolling ball background subtraction algorithm. This rolling ball algorithm is similar to the one implemented in ImageJ. The concept behind the background subtraction is that a local background value is determined for every pixel by averaging over a very large ball around the pixel. This value is then subtracted from the original image with the aim of removing the large spatial variation of the background intensities. The algorithm is controlled by the radius parameter, which determines the radius of the rolling ball in pixels. This value should be at least similar to the radius of the largest object in the image, which is not part of the background. Other functions available, such as create background only, allow us to predetermine the rolling ball radius in relative to the sample object. Meantime, the smoothing function ensures the image data after subtraction will not go below the background, while the light background function allows us to perform background subtraction in transmitted light wide field images, mainly to remove shading issues. The third option to improve your fluorescent images in Widefield microscopy is by means of structured illumination techniques as implemented in Zeiss Apotome tool. Apotome remains the gold standard for optical sectioning in an inexpensive Widefield microscope setup. From the image on the left, we can clearly see that Apotome shows much better out-of-focus blur removal compared to background subtraction and removal of blur with Adobe Lightroom. When a 3D dataset was acquired with Apotome and projected as maximum intensity projection, as shown in image 4 on the right, nuclei that are not seen in the single plane image are now clearly visible in high contrast as structures from another focus plane. This slide shows the principle behind Apotome implementation of structured illumination. What happens is that the Apotome projects a grid structures into the focal plane of your specimen. Then, move it in 3 positions using a scanning mechanism. At each grid position, Apotome automatically acquires a digital image. Then, using a patented algorithm, the 3 images are processed into a single optical section image. The final image that emerges is free of the grid structures with improved contrast and resolution. For better illustration on the implementation of Apotome, let's look at the set of images here. The projected grid becomes visible in the focal plane as a result of specimen features being excited with the structured light. In region where dark grid lines is visible, as pointed out here by the red arrows, this means that the underlying specimen is within the focus plane. But for region where no grid is visible, as pointed out here by the blue arrow, this means that the underlying specimen is beyond the focus plane. The software will then determine the changes in local contrast to differentiate the in-focus structures from the out-of-focus structures before collecting the 3 images into a single optical section. Let us now compare images obtained from background subtraction and Apotome system. What we are seeing here is Widefield images of a flatworm stained in green and red fluorescence. The top row are the single plane images, while the second row are the maximum intensity projection of image stack with height of 160 micron. Images shown in the middle column are processed with background subtraction. When you compare with the Widefield image, more structures are visible in this dataset. However, when you compare with the image from the apotome system, you will see that a lot of details are missing in the image obtained with the background subtraction. In addition, some of the compact green structures on the edges seems to have eroded. Here is another example of comparison between image from background subtraction and image acquired with apotome. What we have here is a 3D rendering Z-stack of a zebrafish stained in blue, green, and red fluorescence. Similar to earlier observation, more structures are visible in the background subtracted dataset when compared to the Widefield image. However, when you compare the image with the apotome system, you will see that a lot of details are missing. The next example here is that of a giant liver float stained with hair staining. The homogeneous fluorescence in the inner part of the Widefield image poses a serious problem for background correction algorithms. As you can see in the background corrected image, some structures remain, but in general, there are too many black spaces between the cells. This problem becomes highly visible when the image is compared to the image acquired with apotome. Another thing to note is the prominent rim around the structures in the background corrected image. This is an artifact from interference in the Widefield image, which is not visible in apotome image. From this slide, we can certainly say that background subtraction will result in loss of information and may introduce artifact to the processed image. This reduces the suitability of background subtraction as it may lead to inaccurate scientific conclusions. The next option is the deconvolution method. This method has been available in microscopy for more than 20 years. It is one of the best described processing methods in microscopy science, and it is based on the complex mathematical model that aims to improve the image quality. There are different types of deconvolution algorithms available, and they all come with their own advantages and disadvantages, basically differing in reconstruction quality and speed. The examples shown here are the images of transfected HeLa cells with Regi protein and counterstained with DAPI and MitoTracker. On the left is the Widefield image, and on the right is the same image after deconvolution using the constraint iterative algorithms. When comparing the both images, we can see that deconvolution has the property to denoise, improve contrast by removing out of focus light, and increase the resolution. In addition, Widefield deconvolution approaches has the ability to reassign photons from the blur to the point of origin, and to restore many structures that resulting in the 3D volume that may have not been visible before. Deconvolution microscopy is therefore also known as signal-inclusive method. In Zen imaging software, we are offering a fully integrated deconvolution module with easy workflow and high processing speed. There are two modes available, the default deconvolution and advanced deconvolution. For the default deconvolution, 4 different methods are available, from the simple and very fast nearest neighbor algorithm to the intensive but slow constraint iterative algorithm. This is the easiest to use deconvolution function without any further settings required, because the software will automatically adapt to the microscope configuration used to acquire the image, and good initial result can be achieved by using a carefully pre-selected set of default parameters. This mode is available in all Zen software license. The advanced deconvolution is available as a paid module, and we offer access to all available parameters for expert users. Here, you can access advanced features such as point spread function settings and spherical aberration corrections. There are over 20 published deconvolution methods available in Zen software to provide the necessary flexibility to cater for your different research needs. Now, let's compare some datasets generated with background subtraction and deconvolution. This slide shows the Widefield Z-stat image of cells labeled with mito tracker in green fluorescence, while the end-binding protein EB3 on the microtubule tip was labeled in red fluorescence. The first row is the maximum intensity projection overview images. The dataset for the background subtraction and deconvolution looks very similar here. Both show improved contrast compared to the Widefield image on the left. However, the differences are becoming obvious in the detail region of interest. When we look at the detail in region 1, structures that are visible in Widefield image can also be observed in the deconvolved image stack. But these structures are completely removed in the background subtracted dataset, no matter how much display contrast and brightness are increased. This shows that deblurring methods such as background subtraction and other similar techniques will erode weak signals and completely remove the signals during background correction, resulting in the loss of information. When we look at detail in region 2, it is clear that the spatial resolution of the deconvolved dataset are much better compared to the background corrected dataset. What we see here is the Z-stat dataset of tumor spheroid stained with blue, green, and red fluorescence. This dataset was acquired with Zeiss Cell Discover 7 Widefield system. The image at the leftmost is the maximum intensity projection of 3-color fluorescence after constrained iterative deconvolution. For the sake of comparison, only a single plane green channel dataset was used. From left to right, what we have here is Widefield image, background subtracted image, and image deconvolved with nearest neighbor and constrained iterative respectively. And the red box in each image depicts the intensity profile across the region. When we extract this profile and compare this value in absolute intensity, as shown in the chart here, the intensity profile from Widefield and background subtraction display a much lower contrast when compared to the profiles from nearest neighbor deconvolution and 3D deconvolution dataset. The high contrast obtainable in deconvolution dataset were due to the ability to reassign photons back to their origin. In this webinar, we have discussed several methods on how to get better fluorescent images with your Widefield microscope. You might ask which method you should be using for your own research needs. This table summarizes the typical suitability of improvement methods for Widefield images relative to each other in terms of effort and quality. For unsharp masking and background subtraction, they do have drawbacks. For example, when large homogeneous structures or weak signals are present, they will erode these signals and result in loss of information, therefore making them non-quantitative. Furthermore, many journal author guidelines either forbid sharpening or caution against it. Both methods may be useful for experimental troubleshooting, for example, to optimize the staining protocol, to find region of interest, or to improve threshold-based image segmentation for subsequent simple image analysis, such as cell counting and area measurement. On the other hand, methods such as deconvolution and optical sectioning like apotome and laser scanning confocal are able to produce high-quality images, and therefore, they are suitable for use in conference presentation, in advanced image analysis, for example, colocalization study or intensity-based measurement, and more important, for publication in journal. This is because apotome and confocal microscope uses the advanced optical setup to allow acquisition of sharp images from single plane and of entire 3D volume. On the other hand, the convolution uses as much information as possible from the imaging system and the sample to allow a more accurate image reconstruction. In any case, when it comes to data post-processing, steps must be reported to journal, and all original must be archived for the reviewer to compare the enhanced image with the originals. It is therefore important for you to choose the correct methods that are needed in your research project. With that, I end my presentation. Thank you very much for your attention. I will be happy to take any questions from the floor.